Welcome everyone. Welcome to the final session for the Polymer Reaction Engineering interactive live session. So today we'll be seeing the questions from assignment 12 and we'll be solving them. Tomorrow there will be a small doubt clearing session. If any of you are interested, you can attend. So let's proceed with today's session. First question is steady state assumption is slow cationic polymerization is valid only if. So it has been asked that what is the steady state assumption in slow cationic polymerization and what are the conditions for it to be valid. So what happens in steady state assumption is that there are instances when the reactions proceed too rapidly. So steady state is sometimes not achieved. So for it to be for steady state to exist, what are the assumptions we require? So first of all, rate of initiation should be greater than rate of termination. So with that, what happens is concentration of the propagating centers slowly increases throughout the polymerization, reaching maximum later in the reaction, and then they decrease. So what happens in this case is that when the rate of initiation is very much higher than the rate of termination, the concentration of the propagating center will slowly increase, which means that the initiator concentration and the radical or the ion which is propagating the reaction will slowly increase throughout the polymerization reaction and it will reach a maximum later in the reaction and it will then start decaying. Next is the rate of if the rate of propagation is constant with the conversion. So what happens if the rate of propagation is constant with conversion is that if the rate of propagation is constant with conversion, its exception will be that only that when the monomer decreases, the initiator concentration, decreased monomer or initiator concentration will affect the rate of propagation. So to maintain that, the rate of propagation should be constant with the conversion itself. So that's why these two are the correct answer. Rate of initiation should be greater than the rate of termination, and rate of propagation is constant with the rate of conversion. Second and third. Next we have is protonic or Bronsted acids initiate cationic polymerization by protonation of the olefin. The anion of that acid should not be highly nucleophilic, otherwise it will terminate the protonated olefin by combination. So what happens in protonated Bronsted acids that initiate cationic polymerization is that whenever the acid mixes together with the monomer unit, then it will form a ionic dipole inside the molecule itself. An example would be like this. So if you have a molecule right here, that is the uh, protonic or the Bronsted acid, which will initiate the reaction with, for example, you have a molecule right here. So this is a molecule, and when it is reacting with the protonic or the Bronsted acid, what happens is your C double bond CH2 will get to position like this. CH3 with A and B end of it. So you can see how the uh, protonic or Bronsted acid will initiate the cationic polymerization by protonation of the olefin. So protonation has occurred. and here this C will have a positive charge on top of it. So because of that, protonation has happened. So in this case, what happens is if the anion of the acid is highly nucleophilic, it will terminate the reaction. So if it's nucleophilic in the sense like it will have a negative charge, what will happen is it will terminate the reaction. The acidic center right here, if it will terminate the reaction. So that's why the anion of that acid should not be highly nucleophilic. So that's why the statement is true. So this question, for a compound to act as a cationic initiator in ionic polymerization, it should be what? First of all, for cationic initiation process, if it is, as we've seen in the next previous question, if it is excessively nucleophilic, it limits the utility of more strong acids as the cationic initiation. So it should be less nucleophilic. So amongst the less nucleophilic is the answer for the question. On top of this, hydrogen halides are ineffective as initiators of cationic polymerization because of highly nucleophilic character of the halide. So that was an example of the hydrogen halides. So that's why the cationic initiator should be less nucleophilic. Only then it should be able to act as a proper initiator for the ionic polymerization process. For a compound to act as a good cationic polymerization initiator, the following properties are required. Choose the correct option. First is it should be highly nucleophilic compound. We have seen in the previous question. No. It should be a strong acid. Example hydrogen fluoride. Again, the example for the hydrogen halides show that they are ineffective as initiators because they are highly nucleophilic. Third one is electroinitiation. Electroinitiation or electroinitiated polymerization involves the initiation of cations formed in the electrolysis of some component of the reaction system. So what happens in this is that some component of the reaction system is formed, and because of the electrolysis, it is possible when there is some monomer solvent or electrolyte involved, or any other added species can initiate the process via electrolysis. So third option is the correct answer. Generally, the amount of energy required to ionize the neutral molecules per unit mole to start ionic polymerization. So basically, for ionization, we need a lot of energy. So you can see that these options, the highest one is 9 electron. So direct ionization will require very high amounts of energy. So that is 9 electron volts or more. And that can be achieved by radiolysis or photolysis. So that's why you need 9 eV or more. Next one is the ionophores which binds to a particular ion and shield its charge from the hydrophobic environment of the membrane, forming a lipid-soluble complex with the cation, which then diffuse across the membrane are classified as. First is mobile carrier ionophores. Second is channel forming ionophores. So what happens with ionophores is that in mobile carriers they bind to a particular ion and shield its charge from the hydrophobic environment. So that is for the mobile carrier ionophore. And they do this by reversibly binding to ion to form lipid soluble complexes which rapidly membrane, diffuse across the membrane, and they catalyze the passive transfer of cations across the hydrophobic membrane. So that's how the mobile carrier ionophores are involved in the ionophoric cationic transfer, which then diffuses across the membrane. So first one is the correct answer. What are the conditions required for? So, what are the conditions required for achieving a narrow molecular weight polymer during the ionic polymerization? So, for this, what you need to do is have a low termination rate and rate of initiation should be equal to rate of propagation. So, because of this, what happens is if the If the chain transfer rate is very high, what would that do is it will just shift the activity of one chain to the other without having a very long chain. So if we want the long chain, termination rate should be low so that the highest molecular weight can be achieved, and rate of initiation will be equal to rate of propagation so that new chains are being formed very quickly. That's which of the following can be used as experimental methods for determination of absolute rates: short stopping of polymerization system or UV visible spectroscopy, addition of chain transfer agent to the polymerization reaction. So what happens in this is UV visible of propagating species during the polymerization process. How does that work is high extinction coefficient of the aromatic carbocation propagating species can be identified with the help of UV visible spectroscopy, and UV absorbance of the system as a function of time allows to determine the initiation rate and the propagating species rate also, which is Kp. So that can be easily achieved. What happens with short stopping is that it is limited by the difficulty of the end groups analysis, since the concentration of the end group can be low. So if the concentration of end group is low, short stopping short stopping of the polymerizing system can be generally difficult. So that's why uh, the experimental methods which can be used to determine the absolute rates are short stopping of polymerizing system and UV visible spectroscopy. What physiological changes can occur in cell due to electrochemical gradient created by ionophores? So what happens is that because of the because of the ionophore and the electrochemical gradient created by them, equilibrium between free ions and the ion pairs shifted towards the free ions due to highly polar solvents involved. Increased polymerization rate will be there, and low polar solvents drive the reaction system towards the covalent species, which does not propagate or propagates more slowly than free ions. And channel forming because of the ionophores, hydrophilic concentration, hydrophilic uh, hydrophilic core to membrane, allowing specific cations to pass through without coming into contact with the interior of the membrane. So osmotic balance can be easily achieved. On top of that, the oxidative phosphorylation and cell segment, which involves the low polar solvent driven reaction system towards the covalent species, which does not propagate or propagates more slowly than the free ion itself. So, which factors can cause changes due to the effects of the reaction medium itself? So, what are the factors which are involved in the changes due to the effects of the reaction medium itself? In counter ions, what happens is counter ions are used when we want to shift the equilibrium between three ions in ion pairs. So, if counter ions are present, it will shift the equilibrium towards the ions due to high polarity solvent. If the solvents are also in. And solvents are very helpful in increasing the polymerization rate. And chain transfer agents are basically additives or they are present in the solvent liquid itself, which propagate the activity of one polymer chain to the other. Subject. Starting from the first question, which of the following compounds are considered as chain transfer agents for redox reactions? So first of all, what is the chain transfer? Chain transfer chain transfer agents are introduced inside a reaction which can advance the radical formation by activating the higher state ions and initiating other species. So amongst these, the popular chain transfer agents for redox initiation are methylamine, aliphatic alcohols, and mercaptans. So this is because they are able to initiate the higher state of ions and for other initiating species also by promoting the radical formation. Methylamine is basically it has an amine group where after the dissociation of the removal of the methyl group it becomes a triamine, and that is the exact reason why it is more reactive in creating the chain transfer activities for the redox initiation. And then similar properties are observed in aliphatic alcohol and the mercaptans, which are sulfur-based groups. In the blank suspension polymerization reaction, the polymer is insoluble in its monomer and thus precipitates, contributing to the formation of irregular grains or particles. So here you can see that we have a schematic right here where we have the organic phase and the aqueous phase, and there is an impeller which is mixing the entire mixture. Uh, in the organic phase, monomers come into picture inside the aqueous phase, and the monomer droplets, when they undergo polymerization, it gives rise to the polymer particles. This kind of polymerization process is the suspension polymerization process, when the particles are suspended in a solution. Now, what happens in powder suspension is that the powder suspension polymerization polymer is insoluble in its monomer and thus precipitates, contributing to its irregular grains. So, and in bead polymerization, what happens is in bead polymer is soluble in its monomer and it is smooth and spherical. Hence the name bead. Because beads are smooth and spherical in nature, that's why the polymerization, this branch of suspension polymerization is called bead. So in the powder suspension polymerization, the polymer is insoluble in its monomer and thus precipitates, contributing to formation of irregular. So the answer for this question is powder polymerization. Moving on to the next question. We have two statements here. Statement one says that chain transfer agents and redox initiation are helpful in the case where molecular weight of the product is to be controlled. And statement two is chain transfer agent results in retardation in rate of reaction. Choose the correct answer. So chain transfer reagents, as we have known that they are known to transfer the activity of one active polymer chain to the other in the redox initiation are helpful in the cases where the molecular weight of the polymer is to be controlled. So this is true that whenever the polymer chain is extending in length, we can simply pass on the activity of the extending chain to the other non-extending chain. So with that, we are able to control the molecular weight in the entire initiation process and the polymerization reaction. So statement one is correct. Statement two is that chain transfer agents result in retardation in the rate of reaction. This is also true because since chain transfer agents are continuously transferring the activity of a single chain to the other chains, the rate of the reaction is quite slow as the activity is being transferred and a single chain is not able to grow to its maximum potential. So that's why statement one and statement two are correct. The correct option for this question is the first one. In dispersion polymerization usually yields polymer particles with sizes in between those obtained by emulsion and suspension polymerization. The nominal particle size in this range is, so if you have gone through the uh, common description of the emulsion and suspension polymerizations, you will know that the entire range of the emulsion suspension polymerization lies between micrometers and millimeters, 1 to 10 micrometers and 10 to 100 millimeters. So in these two ranges, the only one which lies is the 1 to 10 millimeters. So that is the correct answer. So the polymer particle yielded will be between the size of 1 to 10 millimeters. So that is the correct answer for this question. The next question is the compounds which absorb the desired amount of photo energy to reach its excitation stage and finally react with the second compound to generate free radical is called photoinitiation. So this is not correct because the correct term for this is the compound which absorbs desired amount of energy and get excited to generate free radicals is called a photosensitizer. So these are not called photoinitiators, they are called photosensitizers. So the desired amount of photo energy is absorbed by the photosensitizer and it starts generating the free radicals. So this statement is false because it's not called photoinitiator, it is a photosensitizer. Kinetic chain length can be defined as the ratio of the following options. So here we have given three options: polymerization rate by initiation rate, polymerization rate by termination rate, initiation rate by termination rate, or none of the above. So first of all, what is kinetic chain length? Kinetic chain length is the number of monomer units reacted with an active center during initiation to the termination state. So from starting from initiation to termination, the number of monomer units which have reacted with an active center give the kinetic chain length during a polymerization process. And this can be written by the expression of rate of polymerization divided by the rate of termination. So that's why correct answer for this question is option B, that is polymerization rate divided by the termination rate. Because all the monomer units which have reacted with an active center during the initiation to the termination is the entire polymerization step. So polymerization rate divided by the final process, which is the termination rate, will give you the kinetic chain length of a polymerization process. In suspension polymerization, the average rate of energy.
Termination only, na? Termination is the correct time.
Yeah, yeah,
Polymerization.
termination.
Termination. Okay.
Polymerization, yeah.
Yeah.
In suspension polymerization, the average rate of energy dissipation, epsilon, is used to characterize the quality of mixture. In the presence of a dispersed phase, the turbulent intensity, blank, due to the blank in the velocity fluctuation of continuous phase. Select the correct option. So the mixing phenomena usually controls the particle size density. So the better it is mixed, the higher and better particle size density will be forming. So in suspension polymerization, the rate of dissipation is characterized by the quality of mixing. So the presence of any dispersed phase that, during the turbulent intensity decreases. The dispersed phase decreases due to the turbulent intensity, and because of in dispersed phase, turbulent intensity decreases due to decrease in velocity fluctuation of continuous phase. So there are dispersed phase and the continuous phase. So since there are fluctuations in the velocity of the continuous phase, the turbulent intensity, the dispersed phase, the turbulent intensity decreases due to the decrease in the velocity fluctuations of the continuous. So both terms are decreasing. So that's why the correct answer for this is the fourth option. That is, both of them are decreases and decrease. Dispersed phase, in the presence of dispersed phase, the turbulent intensity decreases due to the decrease in velocity fluctuations of continuous. Which of the following types of monomers cannot be used in plasma polymerization for the formation of cross-linked polymers? Alkanes, cyclic or ring compounds, unsaturated hydrocarbons. So for a standard polymerization, polymerization process, none of these can be used since they are not suitable to be used with the plasma, as plasma is a very high temperature polymerization reaction, and alkanes, cyclic compounds, or unsaturated hydrocarbons can create unwanted byproducts during the plasma polymerization. That's why compounds which can withstand very high temperatures are only required for the plasma polymerization process. So none of the above is the correct answer for this. During chain transfer reaction in radical polymerization, the telomerization of polymer occurs. So during chain transfer process, if the rate constant for the transfer reaction is very large, then that of the propagation, while the rate of reinitiation is comparable with the original propagating radical. So in this case, what is happening is when the rate constant for the transfer reaction is very large, than that of the propagation. So it is quickly transferring before it is propagated. So the activity of the chain is transferring before the chain can propagate also, while the rate of reinitiation is comparable with the original propagating radical. So the original radical which was propagating because of the chain transfer, its rate is equal to the reinitiation which is occurring. Reinitiation means formation of new radicals which are initiating the polymerization in other spots. So there will be no effect on the rate propagation itself, but chain length will change drastically at small polymers. Since the chain transfer reaction is very fast, it is not able to propagate properly and it is forming small chains. And because of that, this phenomena is called the telomerization of the polymer. So during polymerization of the chain transfer reaction is very high. At that time, the telomerization process occurs and small polymeric chains are formed. So this happens when the transfer rate is much higher than the propagating rate, and the you can see right here option number B is the correct answer, where KTR, that is the transfer reaction rate, is much higher than the propagation. And we have here Ka is equivalent to the Kp, that is the propagation. So here the initiation radical reaction rate will be equal, reinitiation radical reaction rate is equivalent to the original propagating rate. So that's why option B is the correct answer. KTR is greater than Kp and Ka is equal to Kp. So this is the second option is the correct answer. In radical polymerization, sometimes the premature termination of propagating polymer occurs due to the transfer of hydrogen or other atoms to the propagating polymer from the same molecule, solvent or with the initiator. The new radical formed due to the chain transfer reaction can again initiate the polymerization. This leads to what? So we have four options here. In premature polymerization, one second. So in premature termination of the propagating polymer, which happens, which leads to the decrease in molecular weight of the final product. So there is a decrease in the molecular weight of the final product as compared to the theoretically determined value. So in radical polymerization, if there is premature termination occurring, so the theoretical value of the molecular weight which was expected will not be achieved, and lower value than the theoretical determined value will be formed in the product. So reasons why this happens is because of the transfer of hydrogen and other atoms to the propagating polymer from same monomer, initiator or solvent. So decrease in the molecular weight of the polymer is the correct answer for this question, since the polymeric reaction rate is reduced. I see that Partha has joined us now, so I'll go through the questions once again. Uh, Sir has observed it, like all the questions. So if you have any other doubt, like sir, if you have any doubts, you can ask me, or else I'll start explaining Partha question.
No problem here. Please go ahead. Because actually I was noting all these things. Only I had one doubt, very specifically with respect to this one only,
Hmm.
where chain transfer agents, like where we are having additional radicals, like free radicals ready to give, right? That only we are considering here.
Huh.
That is the justification for this three, no? Option three options.
Hmm. Okay. Okay then. Yeah, yeah. There are only three options. Yes.
Okay, okay. That much only. Other things are clear. And the next one is related to, okay, that is polymerization, bead polymerization, the
Yeah.
powder suspension and powder related aspects.
Hmm.
Right. Okay, this is clear.
So,
This is clear.
like, if you just go through the sir's notes, right, you will be able to understand all of this. Because these are only the process
Yeah,
details.
probably I think here this is for the coming for the upcoming week, I believe.
Yeah, yeah. This is for the upcoming.
Yeah, okay, okay. Otherwise, other things are understandable. Whatever that you discussed is good.
Hmm. Yes. Okay, then I'll just go through the questions.
Shall
That's
I
fine.
take leave here? Actually, there is one more session,
Yeah,
if
yeah.
you don't mind.
Yeah, yeah, sure.
Thank you, thank you,
Sure.
thank you.
Yeah. Okay. Okay, then. So, starting from the first question, which of the following compounds are considered as chain transfer agents for the redox initiation process? So, first of all, what are chain transfer agents? Chain transfer agents are agents which transfer the activity of a propagating chain to the other chain. So this happens, and why is this required is because when you want to uh, control the rate of polymerization and you want to control the molecular weight of the polymer form, this is a very good way to control it, as you won't let the chain to propagate very high at a very high molecular weight, and you can just transfer the activity to the other monomer. So that's why the compounds which are considered as chain transfer agents for redox reactions are amongst these methylamine, aliphatic alcohol, and mercaptans, because they are easily able to transfer the free electrons to uh, other propagating chains. They are very capable in transferring the free electrons, as they themselves are having quite an abundance of electrons which are present there. So that's it. That is the exact reason why the first three are suitable for the redox initiation process. Now, redox initiation process is the initiation process where the polymerization process is initiated relying on free radical producing the oxidation reduction reaction. So that is the redox initiation process. So in that, methylamine, aliphatic alcohols, and mercaptans are used as popular transfer agents for redox initiation. This is a quite normal question because these are just the few examples of chain transfer agents for redox initiations, and you can quite easily identify them from the electronic configuration and how they are able to transfer the electrons to the other propagating chains. If you read about the chain transfer agents and the redox initiation process. In the blank suspension polymerization, the polymer is insoluble in its monomer and thus precipitates, contributing to the formation of irregular grains or particles. So we know that suspension polymerization has two types, powder and bead. So in bead polymerization, what happens is bead polymer is soluble in its monomer and it forms smooth spherical particles. Hence the name bead, because the since it is soluble, it will form smooth particles and it is bead shaped. And since it's not irregular or grain. So the remaining one only is the powder suspension, where the powder is insoluble in its monomer and thus the precipitate contributing to the irregular grains is formed. So that's why powder suspension polymerization is the answer for this question. Statement one. Chain transfer agents in redox initiation are helpful in the case where molecular weight of the product is to be controlled. As I said in the first question, chain transfer agents in redox reactions are usually used to transfer the activity of one chain to the other, and hence it is able to stop the propagating of the single polymer chain to a very high degree, and we can easily control the molecular weight. Statement 2 is chain transfer agents result in retardation uh, re- retardation in the rate of reaction. This is also true because since the activity of one chain is being transferred to the other, the fastness of the reaction or the how fast the reaction is occurring is also hindered because of this. So that's why the rate of the reaction is also affected in a negative way. So that's why chain transfer agents will result in retardation of the rate of reaction. So statement one is correct and statement two is also correct for this one. Next we have is dispersion polymerization usually yields polymer particles with sizes in between those obtained by emulsion and suspension. So if you know about the emulsion polymerization and suspension polymerizations, we clearly know that emulsion polymerization, the particle size lies between 1 to 10 micrometers, and the suspension polymerization is between 10 to 100 millimeters. So somewhere in the middle of that will be the 1 to 10 millimeters. That is the particle size produced in the dispersion polymerization. So that is in the middle of emulsion and suspension polymerization. You will be able to find the answer for this question just by going through the initial descriptions of the emulsion and suspension polymerization process. So because of this, the correct answer for this is 1 to 10 millimeters. The compounds which absorb the desired amount of photoenergy to reach its excitation stage and finally react with the second compound to generate free radical is called a photoinitiator. So the entire statement is correct except the fact that it is not called a photoinitiator, it is called a photosensitizers. And photosensitizers absorb the desired amount of photoenergy and get excited to generate free radicals. So once reaches the excitation stage, it will start generating the free radicals. So this statement is false because it's not photoinitiator, it is called photosensitizer. Kinetic chain length can be defined as the ratio of. So we have been given three options right here. So first of all, we'll see what is kinetic chain length. Kinetic chain length is nothing but the number of monomer units reacted with an active center during initiation to the termination step. So what happens in this is that if there is an active center and if a monomer reacts with it and subsequently many monomers react with it, and if their activity is monitored from the initiation to the termination, that will give you the and the chain formation how of the monomer, if you are going to judge it, that is the kinetic chain length of that polymerization process. And since that is the definition for the kinetic chain length, from there itself you can point out that the polymerization rate divided by the termination step rate will give you the kinetic chain length of a polymerization process. So option number two, if you can see, polymerization rate divided by the termination rate is the correct answer for this question. In suspension polymerization, the average rate of energy dissipation epsilon is used to characterize the quality of mixing. In presence of a dispersed phase, the turbulent intensity due to the dash in the velocity fluctuations of the continuous phase. Select the correct option sequentially. So in suspension polymerization, what happens is the average rate of energy dissipation is used to characterize the quality of mixing. Now, why do we need to do that? That's because mixing phenomena can control the particle size density. So if you are able to control the particle size density through the average rate of energy dissipation, which is used to characterize the quality of mixing, that will be very helpful in maintaining the molecular weight and controlling it throughout the polymerization system. And because of that, it determines the flow and energy field inside the vessel. So because of this, we are able to easily tell that what is the energy dissipation parameter inside the vessel. So when in the presence of a dispersed phase, the turbulent intensity will decrease due to the decrease in the velocity fluctuation of continuous phase. So that is what is happening. So when there is a dispersed phase, in presence of a dispersed phase, the turbulent intensity will decrease. will decrease due to the uh, decrease in the velocity fluctuations of the continuous phase. If there is a decrease in the turbulent intensity of the dispersed phase, which can be attributed to the decrease in the velocity fluctuation of the continuous phase. Which of the following types of monomers cannot be used in plasma polymerization for formation of cross-linked polymers? So in plasma polymerization, you need polymers at very high temperatures. In plasma polymerization, uh, the temperature is very high for the cross-linking of polymers which are required. And that is the exact reason why alkanes, cyclic or ring compounds, and unsaturated hydrocarbons, which are mentioned right here, cannot withstand that kind of agitation, and they are not suitable for this kind of cross-linking process. So that is the exact reason why none of these are suitable for the uh, reaction, plasma polymerization reaction. During chain transfer reaction and radical polymerization, the telomerization of polymer occurs. Now, first of all, we need to understand here we can see that there are different terms being used here: chain transfer reaction and radical polymerization, and telomerization. Chain transfer, we know what is chain transfer. Chain transfer occurs when the activity of one chain is given to the other chain. The active center of the one chain is given to the other chain to stop the propagation of the first chain. And what is telomerization is that when during the chain transfer process, if the rate constant for the transfer reaction is very large, then that of the propagation, when the chain transfer constant is very large than the propagation, while the rate of reinitiation is comparable to the original propagating radical. So what is happening is that there are two processes here. The chain transfer coefficient, the chain transfer reaction coefficient being very larger than that of propagation first, and second is that rate of reinitiation is comparable with the original propagating radical. There will be no effect on the rate of propagation, but the chain length will change drastically, and small polymers will the reason why small polymers are forming is the chain transfer coefficient is very high. So it is quickly jumping to the other monomers before it can grow up to a certain length. And that is the exact reason which is called telomerization, which means that it is forming small polymers and it is propagating rapidly. That is called telomerization of a polymer. So when does that happen? When the chain transfer reaction rate is greater than the propagating rate, and the reinitiation rate is equivalent to the propagating radical, original propagating radical. So which can be described by option number B. Option B, where KTR is greater than KP and Ka is equal to Kp. In radical polymerization, sometimes the premature termination of propagating polymer occurs due to the transfer of hydrogen other atom to the propagating polymer from the same solvent or with the initiator. The new radical formed due to the chain transfer reaction can again initiate the polymerization. This leads to blind. So in radical polymerization, what happens is the process of premature termination of propagating polymer happens, which leads to decrease in molecular weight of the final product. So the molecular weight is decreased since there is premature termination. The polymer chain is not allowed to grow to its maximum potential. And when this is happening,